A group of researchers has just taught AI something astonishing: how to think in parallel. Not just faster, not just bigger, but in a way that feels eerily close to how we, as humans, wrestle with difficult problems. Trying out different ideas at the same time before deciding which one is best. They call it Parallel R1. It comes from Tencent's AI Lab in Seattle, with contributions from several top universities. And once you understand how it works, you'll see why the AI world is both electrified and uneasy. Let's step back. Normally, when an AI solves something, a math equation, a riddle, it follows a single straight line. One step leads to the next. If it stumbles early, it can wander off course and never recover. Humans don't always think this way. We branch out. We explore alternatives in our minds. We compare them, weigh them, and only then lock in on the answer that makes sense. That flexibility, that ability to reason, is what these researchers wanted to give large language models, not just guessing, genuine reasoning. So the question was, how do you teach a machine to do that? They didn't simply make the model larger. They didn't just feed it oceans of labeled data. Instead, they designed a framework that teaches the model to branch out, to explore multiple directions, and then pull them back together. Imagine this. Mid-solution, the model pauses and essentially says, "All right, time to explore." It launches several independent lines of thought. Once they're done, it gathers them, summarizes, and moves forward. It can repeat that cycle as many times as needed. That alone is revolutionary. But the way they train this behavior, that's the real breakthrough. Training AI to reason in parallel isn't simple. Early efforts were brute force. Ask the model for 10 answers and pick the most consistent. More advanced attempts like Tree of Thoughts or Monte Carlo search looked cleverer, but they leaned on handcrafted rules and external scaffolding. The AI wasn't truly learning the skill, it was faking it. Directly training models with supervised examples didn't work either. Why? Because high-quality examples of parallel reasoning are almost impossible to get. Humans don't write out every mental branch. We only write conclusions, and if you generate fake branches with another model, the AI just mimics the style without learning the strategy. Think of chess. Memorizing grandmaster games won't make you a grandmaster. It teaches imitation, not understanding. So, the Tencent team turned to reinforcement learning, the same trial and error process that made AlphaGo legendary. But even here, there was a trap. If you only reward the model for the correct final answer, it cheats. It might skip branching altogether and just gamble on a lucky guess. On the flip side, if you force it to always branch, it wastes effort on easy problems and bogs down. The real challenge was designing the perfect reward system. Here's how they pulled it off. They split the training into 3 stages. Stage 1 was a cold start. Forget hard problems. At this point, the AI just learned the habit of parallel thinking. When to open a special parallel tag, how to branch into separate thought paths, how to wrap them into a summary. To teach this, they used simple math from GSM-8K, a dataset of grade school problems. And here's the clever move. They didn't create examples manually. They used another strong AI to generate them. Out of 7,472 practice problems, 83% produced valid parallel reasoning examples. But when they tried the same trick on a tougher dataset, the success rate dropped to 0. Not one valid example. The lesson? To teach AI the structure of parallel thinking, you must start simple. Otherwise, it never learns the basics. Stage 2, reinforcement learning, again on those simple math problems. This time, the model only got rewarded if it produced at least one proper parallel block and solved the problem correctly. If it skipped the structure or got the answer wrong, it was penalized. This locked in the habit. Parallel thinking wasn't just cosmetic, it was tied to success. Stage 3, the real test. Now the model faced harder math problems from datasets like math. Accuracy was the only reward. By this point, it already understood structure. What it needed to learn was when branching truly helped and when it wasted time. That adaptive decision-making is the hallmark of real reasoning, and the results were dramatic. On benchmarks like AMC and the notoriously hard AIM contest, Parallel R1 outperformed every baseline. Accuracy climbed by an average of 8.5 percentage points compared to strong reinforcement learning models without parallel reasoning. On AIME 25 specifically, accuracy skyrocketed, up 42.9% over the baseline. But the numbers weren't the only story. Researchers noticed how the AI style of reasoning evolved. Early on, it threw parallel blocks in right at the start, a messy brainstorm trying every angle. But over time, it became more deliberate. By the end, the model solved problems in a clean, straight path, then opened a parallel block near the finish, just to double-check itself. No one told it to do that. It discovered on its own that caution, checking your work was the winning strategy. That's unsettlingly human. Now, there were actually two versions of Parallel R1. The first, called Scene, didn't change the model's architecture at all. It simply learned the behavior through training. The second, Unseen, modified the attention mechanism so that each branch was completely isolated until the summary. In theory, the Unseen version was cleaner, smarter. In practice, the simple Scene version often performed better. The stricter version overfit to the easy problems. Tricks that worked on GSM 8K didn't carry over to harder challenges. The researchers had to adjust training, skip some steps, and alternate reward signals just to get it working again. It still produced results, but the lesson was clear. Sometimes freedom beats rigid rules. The reward system itself was another key. When the AI was rewarded only for accuracy, it ignored the parallel structure, using it just 13% of the time. When rewarded only for structure, it overdid it. 80% usage, but terrible performance. The sweet spot came from alternating signals. Most of the time, accuracy got rewarded, but sometimes the AI earned a bonus for using parallel reasoning. This nudged usage to about 60% while keeping scores high. And there was one more twist. Parallel thinking didn't just improve outputs, it changed the learning process itself. Early on, forcing branches acted like guided exploration, preventing dead ends. Later, once accuracy became the sole reward, the model still kept improving even as it used fewer parallel blocks. In other words, parallel reasoning worked as a scaffold, teaching the AI strategies reinforcement learning alone could never reach. So where does that leave us? For researchers, this is a milestone. Parallel R1 shows you can boost reasoning not by piling on more data or scaling parameters, but by teaching smarter thinking strategies. It's about scaling at inference time, not just scaling size. For the rest of us, it's something more unsettling. Machines are beginning to use reasoning strategies that look uncomfortably human. That's the story of Parallel R1. So what do you think? Drop your thoughts in the comments. I'll be reading. And if you found this as fascinating as I did, don't forget to like, subscribe, and share. Thanks for watching, and I'll see you in the next one.